Hello friends, last time we have completed methods of preparation of aldehydes, ketones and carboxylic acid. Now we are going to see physical properties of aldehydes, ketones and carboxylic acid, in which first property we are going to see is nature of intermolecular forces. Now we know that the aldehydes, ketones and carboxylic acids are carbonyl compounds which possesses C double bond O group, that is C double bond O group, in which oxygen atom is more electronegative than that of carbon atom, and therefore this oxygen atom withdraw electron from carbonyl carbon atom by inductive effect, and thus polarization of this CO bond takes place. That is, this oxygen atom withdraw electron from this carbon atom, therefore this oxygen atom acquires minor negative charge and this carbon atom acquires minor positive charge, and thus polarization of this covalent bond takes place. Polarization means formation of positive and negative poles, and thus this carbonyl group in aldehydes, ketones and carboxylic acid is polar bond. That is, C double bond group in aldehydes and ketone is a polar covalent bond. Hence, these compounds contains dipole-dipole force of attraction. That is, here there is dipole-dipole force of attraction is present in aldehydes and ketones and in carboxylic acid also. In case of carboxylic acid, we know that the function group of carboxylic acid is C double bond OH. That is, along with carbonyl group in carboxylic acid there is presence of hydroxy or OH group. Therefore, there is presence of intermolecular hydrogen bonding. Look here, that is, this is CH3 C double bond OH, one acetic acid, and this is CH3 C double bond OH, second molecule of acetic acid. Now here, this OH group is also polar. That is, this carbonyl group is also polar. Now in case of this carbonyl group, this oxygen atom is negatively charged and this carbon is minor positively charged. Along with this carbonyl group, this OH group bond is also polar. That is, this oxygen atom is more electronegative. Therefore, it acquires delta minus charge, and this hydrogen is less electronegative, therefore it acquires minor positive charge. Similar case happens in case of this second molecule of acetic acid, and therefore here, due to presence of this OH bond, there is formation of intermolecular hydrogen bonding. That is, this electronegative oxygen atom get attached to this electropositive hydrogen atom of second acetic acid molecule, and this electronegative or negatively charged this oxygen atom get attached to this electropositive or positively charged hydrogen atom of second molecule of acetic acid, and therefore this formation of intermolecular hydrogen bonding takes place in carboxylic acid, and therefore there is presence of intermolecular force of attraction in both aldehydes, ketones and carboxylic acids. Second physical property, physical state and boiling points of aldehydes and ketones. Now first we are going to see state. Now formaldehyde is a gas at room temperature, while aldehyde or acetaldehyde is extremely volatile colorless liquid. Higher aldehydes have pleasant odor. Acetone is liquid at room temperature and it has pleasant odor, but most of the higher ketones have bland odor. Then boiling point. Boiling point of aldehydes and ketones increases with increase in molar mass. Next, third physical property is solubility of aldehydes and ketones. Now here, when aldehydes and ketones or lower aldehydes or ketones when dissolved in water, they form intermolecular hydrogen bonding. That is, this is carbonyl group of any aldehyde or ketone molecule, and this is water molecule. Now here, this OH bond is polar in water. Similarly, this CO bond is also polar. And due to this hydrogen of water and this oxygen of carbonyl group get bonded with each other by weak intermolecular hydrogen bonding. That is, in water and carbonyl group there is presence of intermolecular hydrogen bonding, and therefore lower aldehydes and ketones are soluble in water. That is, acetaldehyde and acetone are soluble in water. But as the molar mass increases, the hydrocarbon portion of the aldehydes and ketones increases, and therefore there is formation of intermolecular hydrogen bonding with water does not take place, and therefore solubility of aldehydes and ketones decreases with increase in molar mass. Now we are going to see next point, physical state, boiling point and solubility of carboxylic acid. First we are going to see state or physical state. Lower aliphatic carboxylic acid up to 9 carbon atoms are colorless liquids with irritating odor. Higher members are colorless, odorless, waxy solids. The next boiling point. Carboxylic acids have higher boiling point than corresponding alkanes, then alcohols, ethers, etc. or aldehydes and ketones of comparable masses. Next point is boiling point. Carboxylic acids have higher boiling point than those of alkanes, ethers, alcohols, aldehydes and ketones of comparable masses. Then this is due to the formation of dimer. Now here we have seen that two molecules of carboxylic acid, this is example of acetic acid, when two molecules of carboxylic acid come together, they form a dimer like this. That is, we know that the carbonyl group of this carboxylic acid is polar, and here this OH bond attached to this carbonyl carbon is also polar. This is due to the more electronegativity of oxygen atom, and due to this oxygen OH group forms this dipole. Here also there is formation of a dipole in OH group, and when this dipole is formed, then there is formation of intermolecular hydrogen bonding between two acid molecules like this. That is, this positively charged, minor positively charged hydrogen atom get bonded with the carbonyl oxygen of second carboxylic acid molecule, and here similar way, here this is also negatively charged, minor negatively charged, and this carbonyl atom is minor positively charged, and due to this hydrogen atom of one carboxylic acid get bonded with the carbonyl oxygen of second carboxylic acid molecule to form intermolecular hydrogen bonding, and due to this they form dimers. That is, when one molecule or number of molecules of carboxylic acid come together, they form dimer, and thus the boiling point of carboxylic acid is higher than those of alkanes, ethers or alcohols, aldehydes and ketones of comparable masses. Then boiling point of carboxylic acids increases with increasing molar mass. And last point is solubility. Lower carboxylic acids are miscible with water. That is, they are not dissolved in water, but they are miscible in water due to formation of intermolecular hydrogen bonding. That is, these carboxylic acids also form intermolecular hydrogen bonding with water, but solubility decreases with increase in molar mass, and they are soluble, or all these carboxylic acids are soluble in organic solvents like ethers, alcohols or benzene. Next point, polarity of carbonyl group. Now here in these aldehydes, ketones and carboxylic acid, there is presence of a carbonyl group. Now here we know that this oxygen atom is more electronegative than that of this carbon atom. That is, this oxygen withdraws electron from carbonyl carbon atom, and thus there is polarization of CO group, that is carbonyl group, occur, in which this carbon atom or carbonyl carbon atom becomes electropositive, or it acquires minor positive charge, and this carbonyl oxygen acquires minor negative charge. Now this is due to inductive effect also and due to resonance effect also. Now this is inductive effect, and in case of the resonance effect, this pi electron, that is this carbon, is bonded to this oxygen atom by a double bond, in which one is sigma in bond and second is pi bond. Now these pi electrons get shifted on this oxygen atom due to more electronegativity of oxygen atom, and thus will get the structure in which this carbonyl carbon acquires positive charge and this oxygen atom acquires negative charge. That is, these B and C structures are resonating structure of carbonyl group, and thus the resonance hybrid of this carbonyl group is C, minor positive charge, here oxygen, minor negative charge, and they are bonded like this, that is by dotted pi electrons. That is, these pi electrons resonate from carbon to oxygen atom. This is resonance hybrid. Now from this structure A and D, here on this carbon atom there is positive charge, here also on the carbon atom there is positive charge. That is, this carbon atom, carbonyl carbon atom, which acquires minor positive charge, is electrophilic in nature. That is, it is electron loving in nature, and therefore it attracts nucleophiles towards itself in a chemical reaction. Next point, we are going to see reactivity of aldehydes and ketones. Now here aldehydes are more reactive than that of ketones towards nucleophilic attack. Now here this can be explained on the basis of electronic effect and steric hindrance. Now first we are going to see influence of electronic effect. Now here this is aldehyde molecule and this is ketone molecule. Now in case of aldehyde molecule, CO group, that is carbonyl group, is bonded to alkyl group and hydrogen atom, and in case of ketone, this carbonyl group is bonded to alkyl group, that is two alkyl groups. Now here these two alkyl groups are bulky group and they are electron donating group, that is they donate electrons towards carbonyl carbon by plus I effect, that is positive inductive effect. And due to this, the electron density of this carbonyl carbon increases, and therefore this, due to increased electron density, nucleophilic attack does not, or nucleophilic attack is less possible, or there is less possibility of nucleophilic attack in case of carbonyl carbon of ketone. This is due to plus I effect of two alkyl groups. But in case of aldehydes, this carbonyl group is bonded to only one alkyl group, and therefore here this carbonyl carbon is less electronegative than that of this carbonyl carbon of ketone, and thus nucleophilic attack is possible in case of aldehydes, and therefore aldehydes are more reactive than ketones towards nucleophilic attack. Now second reason is steric hindrance. Now steric hindrance, that is in case of ketone, this carbonyl group is attached to two bulky alkyl groups, and due to steric hindrance, nucleophilic attack on this carbon atom is not possible due to steric hindrance. But in case of aldehydes, there is only one alkyl group. That is, here there is presence of hydrogen atom, and therefore nucleophilic attack can be possible in case of aldehydes, and therefore aldehydes are more reactive than ketones towards nucleophilic attack. Homework for you. There are two questions. First question is, how will you convert? Bring about all these three conversions. And question number 2, predict the products. There are 5 questions. Write down the complete reaction and predict the product. Question number 3. Write reaction showing conversion of ethane nitrile into ethanol. Question number 4. Predict the product. Question number 5. Name the product obtained by reacting toluene with carbon monoxide and hydrogen chloride in presence of anhydrous aluminum chloride. Question number 6. Write reaction showing conversion of benzonitrile into benzoic acid. Question number 7. Arrange the following compounds in increasing order of their boiling points: formaldehyde, ethane and methyl alcohol. Write the answers of these questions in your notebook and submit the PDF of this homework on Google Classroom. Thank you.